Welcome to Radiography Professor Explains. I'm Dr. Delia Lofton. In this lesson, we'll discuss the image signal, pre-processing, post-processing, and examine how each stage influences the final displayed radiographic image. When you make a digital radiograph, the image that appears on the monitor is not simply the raw information captured by the detector. Let's take a closer look at what happens behind the scenes. Between the X-ray exposure and the final displayed image, the system performs several important steps to ensure diagnostic quality. Before the image is displayed, the imaging system converts, corrects, analyzes, and processes the acquired data to produce the final image you see on the workstation. It all begins with the image signal. The image signal begins with the remnant X-ray beam. After X-rays pass through the patient, differences in tissue attenuation create variations in the number of photons reaching the detector. The detector converts this radiation information into electrical signals. Areas receiving more photons produce a stronger signal, while areas receiving fewer photons produce a weaker signal. These variations in signal intensity contain the anatomical information that will eventually form the digital radiographic image. Dynamic range is the range of X-ray exposure intensities that a digital image receptor can detect and accurately convert into image data. Digital detectors have a wide dynamic range, meaning they can respond to a broad range of exposure levels, from relatively low to relatively high. This wide range allows the detector to record a massive amount of data, far beyond what the human eye can see. A high signal-to-noise ratio is critical. If the signal is too low, quantum noise dominates, resulting in a grainy image. Once the raw signal is captured, we move to pre-processing. Pre-processing refers to the corrections and initial processing performed on the raw image data before the image is presented for diagnostic viewing. These operations are generally performed automatically by the imaging system. Pre-processing also includes automated corrections performed to fix inherent detector flaws. The first step takes place at the analog to digital converter, or ADC, where the electrical signal from the detector is quantified into digital data that the computer can manipulate. Techniques such as flat fielding and dark noise correction remove artifacts caused by variations in detector sensitivity or electronic interference. Next is the processing stage. This is where the computer uses mathematical algorithms to prepare the image for human eyes. As the system prepares the image for display, it also performs histogram analysis, identifies the values of interest, applies automatic rescaling, and uses a lookup table to help determine the final grayscale presentation. These algorithms ensure the image has the correct contrast and brightness. These concepts are explained in detail in a separate Radiography Professor Explains video, so we will not cover them further here. Processing includes techniques like edge enhancement, which sharpens the boundaries between tissues, making fine details easier to see. It makes the borders of anatomical structures appear sharper and more defined. However, this post-processing cannot create true spatial detail that was not captured originally. Edge enhancement increases the visibility of boundaries between structures with different pixel values. The computer identifies areas where pixel values change rapidly. These represent edges and increases the contrast between adjacent pixels at those boundaries. Edge enhancement improves perceived sharpness, not the actual spatial resolution of the acquired image. Equalization, or dynamic range compression, ensures that both dense bones and soft tissues are clearly visible in a single image. Finally, we reach post-processing. These are the tools that you, the technologist, use at the workstation to optimize the image. Windowing and leveling allow you to manipulate the brightness and contrast of the image to highlight specific anatomy for the radiologist. Zooming, rotating, and proper anatomical marking are all vital post-processing steps that facilitate a more accurate diagnosis. Image stitching is a post-processing technique that combines two or more overlapping radiographic images into one continuous image. It is commonly used for full spine, scoliosis, long leg, and leg length examinations where the anatomy is too large to capture in a single image. However, remember, digital processing is not a magic wand. It can optimize a good signal, but it cannot fix a poor exposure. In the image on the left, a sufficient number of X-ray photons reach the digital detector. Because the detector received an adequate amount of radiation, the useful image signal is strong compared with the amount of noise. This produces a higher signal-to-noise ratio, or SNR. Notice that the image has a relatively smooth and uniform appearance. With less visible noise competing with the image signal, anatomical structures and subtle details are easier to visualize. Image on the right, quantum model, too few X-ray photons reach the detector. This is commonly associated with underexposure. When fewer photons are available to create the image, statistical fluctuations in the number of detected photons become more noticeable. This produces quantum noise, also called quantum model. As quantum noise increases, the signal-to-noise ratio decreases. The image develops a grainy or mottled appearance you see here. This noise can interfere with the visibility of subtle anatomical structures and potentially obscure important diagnostic information. If your initial exposure is too low, the computer will attempt to stretch the data, but it only results in quantum model. Noise often appears as random pixels that are much lighter or darker than the pixels around them. A smoothing algorithm examines a pixel and its surrounding neighborhood, then recalculates the pixel value based on those nearby values. In the example, the center pixel, 180, is very different from its neighbors and may represent noise. The smoothing algorithm averages or weights the surrounding pixel values and replaces or modifies that unusually high value. Smoothing is an image processing technique used to reduce image noise, grainy appearance, and create a more uniform appearance. It is important to mention smoothing does not correct underexposure. If quantum model results from too few X-ray photons reaching the detector, post-processing may make the noise less noticeable, but it cannot restore image information that was never acquired. Another digital post-processing function used is cropping, automatic shutter, or masking. This feature is used to remove or hide unwanted portions of the displayed image. And most importantly, we must discuss the ethical responsibility associated with post-processing. Digital radiography gives us powerful tools to modify how an image is displayed. We can adjust brightness and contrast, apply edge enhancement, use electronic masking, and crop an image. These tools should be used to improve visualization of the acquired information, not to misrepresent what was actually captured. The radiographer should never manipulate an image in a way that adds, removes, conceals, or misrepresents clinically significant information. Using electronic cropping to hide poor collimation is unethical. It obscures the fact that you irradiated unnecessary tissue. Collimation affects patient exposure. Cropping affects image display. Cropping should never be used as a substitute for proper collimation. Excessive cropping or electronic masking could conceal anatomy or evidence of poor collimation. Excessive enhancement could create artificial edges or obscure subtle findings. Other inappropriate manipulation could potentially make anatomy or pathology appear different from the original acquired data. This is why maintaining access to the original image data is so important. Post-processing should preserve the integrity of the diagnostic information and follow institutional policies and professional standards. To summarize, the journey from exposure to display is a blend of physics and math. Your job is to provide the best raw data. Maintaining technical integrity ensures the highest quality diagnostic images for patient care. Precision and integrity matter. Thank you for joining me on Radiography Professor Explains. If you found this lesson helpful, be sure to like, subscribe, and share. And don't stop here. Check out my other videos on digital radiography, where we explore topics such as digital image receptors, image processing, histogram analysis, and rescaling. Keep learning, keep practicing, and I'll see you in the next video.